From the Library of Congress in Washington, D.C.
Good morning. My name is Jennifer Harpster. I'm a reference and research specialist with the Science, Technology, and Business Division here at the Library of Congress for 2 more weeks. And as she said, I'm going to UC Davis, and I'm going to do their astronomy and physics out there. So you can't take me away from astronomy. I'd like to welcome you to today's program, New Horizons, Journey to Pluto and Beyond. This is our final program of the 2015 series, presented through a partnership between our division and NASA Goddard Space Flight Center. And next year will be our 10-year anniversary. So yay. It's my pleasure to introduce today's speaker, Dr. Dennis Reuter, an astrophysicist with an emphasis, I'll have to say, on planetary studies. He is also co-investigator for the New Horizons mission and the instrument scientist for RALPH, a color imager and infrared spectrometer on the New Horizons spacecraft. Now, pairing with RALPH is another instrument on New Horizons called ALICE. We will better understand the composition of Pluto and other objects in the Kuiper Belt by ALICE and RALPH. And yes, scientists have a great sense of humor. So I'm not sure if you caught the RALPH and ALICE pairing. If you did not, it is a reference to the 1950s TV show The Honeymooners. Dr. Reuter received his undergraduate degree in chemistry from the Rensselaer Polytech Institute, or RPI, and his doctorate in physical chemistry at UC Berkeley. He has been at NASA since the 1980s and has received numerous exceptional achievement awards for his work. And he also has an asteroid named after him. Asteroid 4706 is Dennis Reuter. I think I want a job like that where I get an asteroid named after me. Before New Horizons, Dr. Reuter was a laboratory scientist studying spectra of Earth and space, using heavy equipment in his lab, and then he began to develop spectral instruments for robotic space exploration missions. And I think we have a little bit of show and tell of some stuff that is on New Horizons. He's also, or has been, involved in 5 space missions, and among them are Landsat 8 and 9, New Horizons, of course, and OSIRIS-REx, which is super exciting if you haven't heard about this mission. It's set to launch in September of 2016 to the asteroid Bennu. The mission will bring samples from Bennu back to Earth, and that will be in 2023, maybe? So we'll have to schedule that in. Hopefully next year we can have somebody come in from NASA and talk about OSIRIS-REx. Today we'll learn about the New Horizons mission and explore the Kuiper Belt in an area of space that we haven't had a chance to look up at closely before. Dr. Reuter is going to highlight some of the close-up images of the Pluto system and talk about the science behind it. These high-resolution images tell incredible stories and have created a lot of excitement in the scientific community and the public. They're going to help us understand the composition of the bodies of the Kuiper Belt and how those compositions vary, but they're also going to help us better understand the origins of the solar system. So let's get to the Kuiper Belt and learning about New Horizons, and join me in welcoming Dr. Reuter to the Library of Congress.
Well, thank you very much, and I guess I should say that I'm lucky to be the last one because you won't be here, and so it sounds like everything's going to go to heck. Okay, as she said, I'm Dennis Reuter. Now, I'm a co-investigator on the Pluto mission. There's roughly 25 or so science co-Is, but there's a much larger group of people working on it, collaborators. I'm going to, as you see, we'll talk about the results we're getting, but I will talk a little bit about the instrumentation because, you know, that's my thing. But when I'm giving this talk, please bear in mind that everything you're seeing really depends on the efforts of a huge team. The people who built the instruments, the people who built the spacecraft, the people who ran the spacecraft, who actually planned the operations when we get there. You know, the companies that made the components. This is sort of a national type effort, and it's common for these type of missions that, you know, we have contributions from all over the country, university, government, industry. So I'm very privileged to be part of this, and I thank you for funding it. Now, New Horizons, it completes the exploration of the classical solar system, and I'll get to that in a little bit. But, you know, we've gone through all the planets. Now, there's still a lot to learn from all the planets. Every time we go to Mars, we learn something new. Every time we go to someplace else, we learn something new. I'm sure when we go to Bennu, we're going to learn something new. And we have an instrument on Bennu that's kind of based on, or excuse me, on Osiris, that's kind of based on the technology we developed for New Horizons. But now we're sort of, we finished that just sort of initial exploration part. Now we can really go back and start looking at everything in more detail, and as we already are, but perhaps we'll start to look a little bit more in detail at the farther out parts of the solar system. And that's what New Horizons also did, was it started the exploration of that part of the solar system. Now this is an area that has been around since the beginning of the solar system. It's very pristine. It hasn't been near the sun, so it hasn't been affected by the various things that the sun puts out. Very pristine material. So if you want to go and see what the solar system was like 4.5 billion years ago, well, that's a good place to go, because it really is maintaining that character. The closest approach was just this last July. Turns out that happens to be my wedding anniversary also, July 14th. So my wife was very understanding. I appreciated that very much, because we were not at home. It also was the 50th anniversary of the first transmission of pictures from a spacecraft, Mariner 4, from a planetary. So it was kind of fitting that way. And the results, as you'll see, demonstrate why it's important. It's very important to have the ground-based observations. You know, you spend time, you can go out, you can look at things for quite a while. They just add a huge amount to our understanding. But until you get up to the thing and say, oh my goodness, look at that little spot over there, you really don't understand the thing. And that's what going to these moons or these systems are like. And Pluto helped. Pluto could have been just sort of boring. It decided to be an incredibly diverse and exciting object. And, you know, it's a rock star. I suppose I should say it's a rock ice, because it's an ice star, I should say. So it's cold out there. Well, the mission history, the first concept for what eventually became New Horizons was put forth by Alan Stern and other folks who were on the New Horizons team back in about 1989. In fact, he gave a talk at Goddard talking about a possible Pluto mission. And there were a whole bunch of iterations. There was, somebody was asked earlier, there's an iteration where there were going to be 2 spacecraft, because when we fly by, Pluto has a 6-day rotation period, and so when you get up close, you're going to see whichever side you're close to. Well, if you want to see both sides really good, you have one go by and then another one go by 3 days later. Well, that would have been nice, but you know, it's expensive and da-da-da-da-da. And so the things would come and go and come and go. We got involved at Goddard back in about 1993 or so, because one thing that's characteristic of all these is that you want really light instrumentation that's very capable, because in order to get out to Pluto, you want to go fast. And to go fast, that means you just can't have a whole lot of mass, so you want to have light instruments. And I'll show you, you know, sort of the size of our instrument. You'll understand why it's light. But the New Horizons mission was eventually proposed, and the proposal accepted in November of 2001. So that's when we really started on this. Now, 2001 to 2006 sounds like 5 years, but to go from, oh, I don't have anything, to here, I've launched it, that's a lot of work to do in 5 years. So this was a very intense period of time. It was also the first of the New Frontiers class of mission, which is also what OSIRIS-REx is. It's a sort of the largest principal investigator type mission there is. Launch was from Cape Canaveral in 2006. It was the fastest thing ever to leave the Earth. That picture I had up at front was of the launch, and it was like, oh, there it goes. I mean, it was cloudy, so the whole launch that you could see things was very short, but it was very exciting. We had a Jupiter flyby in February 2018. So basically, 12 months, 13 months after launch, we're at Jupiter. Well, usually it takes years to get there. It took us 9 hours to get to the moon. The Apollos took days. It's moving fast, right? Again, because you want to get there. Now at Jupiter, we got a gravity assist, got us out to Pluto faster, but we also got to practice the type of things that we're going to do at Pluto. And we got some science out that people hadn't seen before. And there were publications on it. It was very exciting. We crossed Neptune's orbit just, about a year and a half ago, and got there at, started to take data that was higher resolution, higher spatial resolution than ever been taken before in the May time frame, and then obviously the closest approach just blows everybody away. So here's our solar system. We're all used to the 4 inner planets. We live on one. We all know about the 4 gas giants. Those were the ones that were visited by Pioneer and Jupiter. The asteroid belt, well, that's, small particles or small objects, kind of like what you see out at the Kuiper Belt, but they've been in close, and so things have happened to them. And now we get to Pluto, and Pluto is at the edge of the Kuiper Belt. That's that new zone that's of the pristine material, and that's what we want to be studying now and in the future, and I'll talk a little bit about that. So the Kuiper Belt, there is a sort of a spherical cloud of objects called the Oort cloud, and that's been around forever, but it's way out. The Kuiper Belt is flat, kind of like the solar system, because when things were condensing down, the whole system condensed down, and then the planets would go and make themselves out of that material. Well, the Kuiper Belt did the same thing, but it tended to make smaller objects, and so those things are still there. Pluto is very large for the Kuiper Belt. We've only found one that may or may not be larger. It's since it's hard to tell. You see a speck of light, and you sort of say, well, I'm going to tell you how big it is, about how bright that is, and how far away it is. But then if the surface reflects more light than you might expect, then suddenly you've got a connection between the size and how bright the surface is. So there are assumptions that are made, but Pluto and Eris is about the same size, but much larger than most other objects out there. So here's our prime target. Now, when we were proposing this, it was Pluto and Charon, its moon, that was found in about 1967. Pluto itself was, of course, discovered by Clyde Tombaugh, in 1930, by looking at pictures, flashing them back and forth and trying to see that one little spot that moved. I'm glad he did it. I wouldn't want to do it. But at any rate, when we were first proposing, it was Charon and Pluto. By the time we launched, there was Nix and Hydra. By the time we got there, there were five moons: Charon, Nix, Hydra, Erebos, and Styx. And this again was found by ground-based observations. But now, as we were going out, suddenly we're changing our design, because there's these objects out there we didn't know about. We want to include them in our observation. So it tells you that the process of designing the encounter was continual from launch. This is the relative size of things. So Pluto, that's the big guy, but it's still pretty small. And then the little guys are really quite little, all right? But they're still important. They still they have information about the system, about what went on out there. Some of them are rotating around really quickly. They're not what we expected. By the way, nothing is what we expected. Our mission objectives. Well, I can go through each of these. We had the Group 1 objectives. Those were the things that you had to do. And the Group 2 objectives, those were the things that you really wanted to do. But if it meant you couldn't do a Group 1, you didn't do a Group 2. And the Group 3s are those things that you do if you have a chance, right? But basically what they come down to is we want to understand, what does the surface look like? What is the surface made of? How does the surface interact with the atmosphere? Pluto has an atmosphere. It would not be much if you went out there. You wouldn't feel, it's about a millionth of what's going of the Earth's atmosphere, but it's there, and it's supported by stuff coming off the surface. So there's still transport going on, the same type of processes that go on the Earth, except at 40 Kelvin. Considering that nitrogen freezes at about 50 Kelvin, you can kind of get the idea of what it would be like if we were on Pluto. There would be no air here. I mean, it would just be stuff on the ground, right? Ice. We look at we look at the ionosphere. We look at the ions. We've chosen the instruments to really be able to sample the entire characteristics of the atmosphere, the surface. We even use the radio communication to get the idea of the mass, and we can look at the surface and see how much power it's putting out in the microwave, and that tells us what the temperature is. We can also use the infrared to get a measure of the temperature in an interesting way I'll talk about a little bit. So we're trying to understand the system as if it were, if it was the Earth, right? I mean, this is the type of thing you'd want to know about a planet. So the spacecraft, it's about the same size as a baby grand piano, and you saw it sitting on a rocket that's 300 feet tall, and it's just this little tiny thing up there going out as fast as it can. It's powered by a plutonium reactor. Now, it's just really, it makes it warm and it generates electricity. Problem is at Pluto, you've got roughly 1,000th of the amount of light that's from the sun as you do here. So, you really can't generate much power, or you need a kilometer-sized solar cell to do so, and it's a little hard to get that out there. So the instrument complement, so again we have LORRI, which is a high-resolution imager, and then we have MVIC and LISA, and those are the components of Ralph, and those are, it's a moderate resolution imager, but it also has colors. That's what MVIC is. And then LISA is the spectrometer. It's the thing that looks in the infrared, and when light strikes an object, parts of it, some of its wavelengths get absorbed, and those wavelengths that are absorbed tells you what the material is made out of. And that's why we look on the infrared. It tells us what the material is on the surface. There's a UV spectrometer. That's primarily for looking at the atmosphere. And then there are these particle swap and PEPSI, which are plasma instruments. They're looking at the solar wind and also the heavier ions that are at Pluto. And then there's a student instrument called the Verner-Berti student dust counter. And that was added at the end. It was very successful. But basically what it does is it looks for particles hitting it and counts how many there are. And so you get a measure of how many dust particles are out there. This is what the spacecraft looks like. It's that little thing up at the top. This thing underneath is the third stage rocket. And that goes on top of the spacecraft. And this all fits into this little area on the top of that thing that you saw was much larger. The spacecraft, they separate after launch. And actually, this guy went to Pluto too, the rocket engine. It doesn't have anything on it. We just know it followed around. But here's the eyes and ears. Usually you don't talk about things having sound in space, but like I said, the dust counter really looks at things hitting it. So it's kind of an ears. It's kind of motion of something. There's Ralph, and Ralph is about this big, and I'll show you a picture of that. There's the Ralph instrument, and this is what's interesting about it. It's two spectrometers in one. It's two cameras in one. The optics in front feed two focal planes, two detectors, kind of like what you have in your cell phone, for taking pictures. But the infrared one is sensitive to infrared light, and this is stuff that was done back in the early 2000s, so it's not as high tech now. We had a 256 squared array. JWST is going to have 4,000 pixel squared arrays, so things have changed, but this is what we were working with. This is the spectrometer that's on Ralph. That's the LISA spectrometer. That gives you an idea of what I'm saying is, and this was a concept that Don Jennings and I came up with, and a lot of other, as we found out later, came up with also. But you basically put this in front of the detector, and the wavelength changes as you go along here. So a given row only sees a given wavelength, right? And you can kind of see this. This is actually not the material that we use. It's sort of an engineering version, just to the people made to show that they could make the coatings. But actually I have some that, if you look at lights and stuff, you can see the rainbow. And if you look at fluorescent light, you can actually see the atomic lines coming out. Okay, so we have both of these things going on. By the way, everything that's done on the spacecraft, we don't have any mirrors moving around or anything. The spacecraft has to move to look at things. So if you want to look at Pluto, you look there, and then if you want to look at one of the moons, you look over here, and then you look back here, and then, so this is the type of planning that goes on. Now on the closest approach day, on 2 days before, 3 days before, okay, we'll look at Pluto, we'll scan it, great. Move around and look at the other ones. On the closest approach day, it's like, okay, I got to do this. Oh, no, we're moving a lot. And I'll show you a movie that actually shows what we did. You'll be amazed, actually. I Again, this is the spectrometer, so this is the visible one. Oh, I forgot to bring a pointer, I always do that. Here, this is the visible one. And it is like long CCD arrays, so they're like 5,000 pixels wide. And then this is our infrared, the 256 by 256. And this is that filter on top of it. There are actually two segments. There's a higher resolution, higher spectral resolution segment, and a lower spectral resolution segment. And this higher spectral resolution has a really cool application. I'll explain in a little bit. Okay, so this is the composition information that we've got. The 4 visible filters, we get the color out of that, but we also have one that looks at a band of methane. So it gives us complementary information to Ralph Lisa, which looks at a whole bunch of bands of methane, a whole bunch of absorption features of methane. And this is the characteristics. And basically what it's saying is there's about 250 colors, if you will, in the infrared that we look at in the visible part. Now the high resolution, that's nitrogen absorbs. You know, I mean, it's not a strong absorber, but if you put meters of nitrogen, solid nitrogen on the surface, and that's kind of what Pluto has, you get weak absorption features. Turns out that the shape of that absorption feature is determined by what the temperature of the ice is, and that's what we use that little high resolution segment for. So we're actually using spectroscopy to tell us the temperature of something that there's no way we could get, the amount of radiation coming at 2.5 microns from a 50K source is 0. There's just nothing coming out. But we can see from the visible, from the reflected solar light, what the temperature is by looking at the spectrum. Remember, well, I'll give you an idea. These are the type of resolutions we're getting. So they're kind of on the order of a kilometer per pixel or better. In fact, Lori gets down to 10 times better than this at some positions, but it doesn't get the whole surface. That's why we had to do sort of a combination of things. But getting down to less than a kilometer on an object that's been seen at, I'll exit that in a second, but much lower resolution is very important. Now this is our mission profile. Again, we launched in 2006. We go by Jupiter, get the gravity assist, we get out to Pluto Charon, and now we're looking out as we go along, and there's another chance that we'll be able to do another observation of another Kuiper Belt object. I'll explain that a little bit at the end, but it's not part of the plan yet, but we're trying to propose that it will be. Well, that first image is what you saw from the ground. That's the best image that we had of Pluto before we launched. That's from the Hubble, actually. It's not from the ground. It's our best thing. That's what we get when we get close to Pluto. That's the heart feature that we were reported so often. And even at the heart feature, now you can see that, hey, they do correspond. I mean, where that heart feature is, it is a little brighter. Where the dark areas is, it is darker. But boy, you really don't see the resolution that you get at that. And that's not the resolution. We actually get higher than that. I have to have a picture that fits on the screen. And I'll show you some higher resolution things. So this is what you get by going someplace. Right? This is the ground. And then you get out there and you see this, and all of a sudden you're saying, well, goodness gracious, there's things all over the place here that are different. And this is, when you put the colors in, you start seeing composition and so on. So here's some New Horizons of results. We didn't have any idea what we were going to see when we got there. When we got there, what we saw was not what we expected. Now, I know it sounds odd, but you kind of expect, well, okay, it'll be a solid feature. It'll look kind of like the asteroids do or something like that. No. I mean, basically every time we get an image down, somebody's saying, what the heck, or words to that effect, is that image? It's just been amazing, the type of things we're finding. We see things and it's not, oh yeah, I understand that. It's, golly, that doesn't seem to make a lot of, because now all of a sudden you're trying to understand things that we've never seen before. Very diverse surface. Evidence of dynamic processes, including nitrogen flow, solid nitrogen flow. I mean, kind of think of that. It boggles the mind that we're talking about processes that happen on Earth, but they're happening at 40 Kelvin on things that are solid nitrogen and solid CO and mixed with solid methane. A lot of different surface compositions are evident, and they're connected to the geology and so on. Atmosphere with multiple haze layers. Who expected that? It's got a blue sky. Yeah, I expected it was going to have a blue sky, right? On and on and on. And the first paper that came out in Sciences. If you're interested, it's an excellent paper, and I would, if you're interested in finding out the real details, that would be a good place to go. Now, I'm going to talk in the pictures that are coming that are going to be more detailed. I'm going to use place names. They're informal. They're not agreed to by the IAU or anything like that. So, just keep that in mind. Well, there's Pluto and Charon in color. And you notice right away that Charon looks kind of smooth, except there's this weird little red spot on top. Where the heck did that come from? Oh, it looks like it's possibly in a depression. Does that mean that Charon has been hit? Maybe. There's this area on Pluto. Oh, look, there's craters all over the place. Over here, up there, it's flat. What's going on there? You tell me. We'll all know. We have theories, but is that a surface that's being refurbished, or is there something coming up from the underneath? This is the image we took on as we left the thing. Look at that. I mean, there's hazes in the atmosphere. This looks like what you'd see, if you looked at the Arctic in the Earth, right? Mountains. That's a very dynamic thing. It's not kind of what we expected. 3-kilometer tall mountains next to flowing glaciers. Sure. Now, as you get to the edge of where the light is hitting, you start to get effects that are showing you the height of certain objects, because now light is coming along and it hits a mountain that's up here. Well, now it makes a shadow behind it. Those are called crepuscular rays. You see these in the Earth all the time. You go out and look in the sky, and you'll see these little spots of rays of light. Well, that's the type of thing that's causing this. Usually, maybe it's a cloud that's in a way that's not letting light go by, and you see light from the other areas. But yeah, you can see this. There's light coming in, and now there's this shadow behind it. Now, this helps us tell how high the thing is, but it also tells us, again, this is a very interesting world. Why is Pluto red? Well, one of the things that people have talked about is tholins. And basically tholins are, you take methane and CO and nitrogen, and you throw solar radiation and radiation from hydrogen lines and cosmic rays at it for 1 billion years, and it causes chemistry to happen, and you get basically gunk. Right? But the gunk has colors, and that's what we think is going on here. But you'll notice that, again, there's that region over here with the craters, with also very interesting other features. That's lots of craters, and then there's this flat area, and it's white, and the other stuff is sort of reddish, and really indicates that something different is going on. So this is that area over there. We think it's older, darker. It's been, we can see the craters. We think it's been more processed than this Tomball regio. Again, informal names, but obviously named after the discovery of Pluto. A nice bright feature that's crater-free. Now we'll start to look at some specifics, areas of this Tomball regio. First we'll look at number 1. That's ice flow. Right? You look up there. Look at that. Nitrogen flowing around mountains. That's what you'd see in Alaska if Alaska were 300 Kelvin colder, when we wouldn't want that. But you're also seeing a polygonal cells. What are those things? Well, maybe they're convection cells. Okay, but not what we expected. And we're still, these are possibilities. We still have to link all the various pieces together to get a full story. But this is the type of information we're getting out from this. And this says this is a very active system. This is at the bottom of that area between where you're getting the cratered surface and where you're getting this new surface. Well, is that because the cratered surface is, the new surface is going backwards and it's leaving the cratered surface behind, or is the new surface going down and covering up the crater surface? Again, lots of possibilities. That's the type of thing we're going to be looking at for the next, well, let's see. The next time Pluto will be where it is now is about 200 years from now. So people will be looking at this for 200 years. I mean, people are still looking at the data that came out of Voyager and Pioneer, and we've sent things back to the objects that they studied. It's going to be a while before something goes back to Pluto. Maybe. We could always hope. Now we have this area of what we call chaos. And what we think these are these are mountains of ice floating in nitrogen, solid nitrogen. Solid nitrogen is a little bit more dense than ice at 50 Kelvin. And you know, if there's some if there's some heat process going on underneath, which we don't know yet, you know, that would kind of explain what's going on here. But we see the interface between the mountains, the sciatic region, the cratered region, and that flat area over there, which, you know, if something's coming up from the surface, if it's convection and stuff is coming up, then that surface is continually being refreshed. We don't see it because it keeps covering the craters. Or some big event has happened, right? We're getting a snapshot in time of something that's been around for 4 billion years. If you look at me, you know, 55 years ago, I will bet you don't say, oh yeah, that's what he's going to look like 60 years from now. So at any rate, you know, so it's challenging, and it's part of what makes the interpretation interesting. Now the color images, now you look at these and you're starting to see, well, now there's specific colors that are associated with the various types of geology you're seeing, right? In other words, the composition is different in those areas that look kind of different if you looked at them in panchromatic. It's sort of a broadband spectrum. Well, again, now we're learning that other things are going on. Is that places where there's been more processing, or is that places where the stuff that was processed was knocked off? You know, again, you can always have two observations or regions. Now you can kind of look at things and say, well, gosh, that kind of looks like what you see on the Earth. And you see glacial islands in Antarctica, and we see a little glacial island there. And by the way, there's streaks coming out over here. They sure look like wind streaks. You know, again, there is wind. It's not high, you know, but again, over millions of years, this is the type of thing that might happen. Right? Don't know yet. That's one of our processes going forward. The heat flow, again, you know, there's the heat flow is what, 0.2% of what it is on the Earth, right? You know, it's not a very strong heat flow. Is it making these things? Maybe, you know, the gravity is much lower. Do we have cryovolcanoes? Now, we didn't see anything. Titan has often been chosen as sort of the Pluto's brother, closer in. And when we went by Titan, we saw, you know, nitrogen geysers coming up. That's really cool. Well, Titan is next to Neptune. There's a tidal force that can drive energy. There's nothing really here that's next to this. You know, Charon is there, but it's small. It shouldn't have that much of a driving force in terms of tidal driving. But you look at these things, and they look like volcanoes, right? There's this vent, and these are sort of saying what the height is, and it's surrounded by an area that looks like something came up and formed, you know, a volcano. We don't see this, but it's very, very suggestive. This is just weird. I mean, you know, the surface is striped. This is what we call the snake skin surface if you follow it around. Again, I'm sure there's an explanation for it, and you know, that's what we'll look at. But when we saw this, people just said, okay, you know, somebody's playing around. I mean, this is it's very strange. And we've gotten some three-dimensional things, and you look at these, and you can see very nice three-dimensional structure. So now we'll get to the part that is the compositional part. This is what we get from the infrared. This is what we're going to relate to the structure. This is one of the first spectra we got using LISA, and there are two different wiggly lines, and those wiggly lines show you where light is being absorbed in very narrow bandwidths. And you can see they're quite different. This is a nice little flat thing. This is a methane feature. That's what methane does. Methane does that too. So it looks like there's methane here, but there's something else as well. Okay, that can happen when you mix stuff together, or maybe there isn't methane there. It's, you know, again, we're interpreting these things. I'll tell you about the data. But this is cool because I think this is the first spectrum that was ever shown on the Jumbotron at Times Square. I mean, this is, you know, you just don't see that too often. All right, well, now we start to look at other things. Water. Well, this is odd. Here's water. We see it, this nice little streak there, not much there. Remember that mountainous area over there that we think is water mountains? We don't see the water in the mountains, we see it around it. Now what that means is that when we say there's water there, we're seeing pure water spectrum. Now if you look at that first spectrum I show you, remember there was the one that was very characteristic of methane and there was one that was not. Well, there's still probably methane in both, but it's other stuff is either on top of it or mixed in with it, and it doesn't look like pure water. These look like pure water. They look basically what Karen looks like, and Karen is pretty much pure water, except where I'll show you it's not. Well, again, what's going on in the surface? Is the surface producing water there that then is getting covered over? Or is that an area that was covered over and something came and knocked it off and now we're seeing the water again? Here's methane ice absorption. Now, this is just the absorption from LISA. So it's not, you're not seeing any of the visible images. But you see features there. And if you put that over a LORRI image at high resolution, now you see that, oh, look, this stuff, there's a lot of methane in that Sputnik planum, which is where that flat area was. Methane is a volatile. It's something that at Pluto temperatures evaporates, kind of. Takes a while, but you don't see the methane over in this region and where the craters are, and it's very correlated with structural features. Same thing for nitrogen, right? Again, you see that area right there. It's that area where there's a lot of evaporating type material, but again, not over in that dark area, and again, it's associated with features. And again, all these names are made up. Same thing with CO. Now, CO is a little noisier. It's not as strongly absorbing. We haven't got all the data down yet. This will get better as we get more of the data down and we can beat the noise down. But again, you see it's right in that area where you expect the volatile things to be. Not much over anywhere else. And then there's water. Oh, well, no water in that area over there. A lot of it over here. So we're seeing that there's a correlation between the geometry, and in fact, if you remember that picture I showed around that crater where they had that little streak of water, that's this guy right here. You can see that there's the spectra is telling us about the geometry, geology. It's very exciting, but this is not the only exciting thing. There's the other moons out there. Charon. Now, again, we see this structure, this thing that's much bigger than the Grand Canyon sitting down here. Where did that come from? I mean, is that something that happened because something hit at the top and sort of fractured things, and then it made, when something hits, it's going to flip the orbital axis, the rotation axis? Charon and Pluto are kind of like the Earth and the Moon. They're tidally locked, so you always see the same face of Charon if you were standing on Pluto. If you were standing on Pluto, you'd be pretty cold, though, so you don't want to do that. But at any rate, but spectrally, it's pretty bland. It's got water everywhere except where there's ammonia, and where there's ammonia is this area where there's a crater. Well, does that mean that that's a new crater that's gone down and let the ammonia out, or is something been let out that has formed ammonia after a while? Is that a new thing? Is this some way that we can possibly date impacts? Again, this combination of composition and geology is really telling us a lot about what's going on the surface, which is an active surface, something that we hadn't expected, or we hoped for, but we hadn't expected it to be this level. Now we got the Charon on the small moons, and basically you're seeing, we don't get as close to them as we get to Pluto and Charon, because they were the objects that we were going for. And if you're going to choose whether you get Charon and Pluto or one of the small moons, you're going to go with Pluto. So we didn't really move anything around. We did actually, though, once we started to see all these moons, somebody said, oh, wait a minute, somebody meaning Alan CERN, that does this mean that now all of a sudden we have to worry about, are we going to hit something? Right? So we spent a fair amount of time doing a lot of modeling saying, well, if material is coming off Pluto, is where we're going safe? If we start to see something as we get close and we start to see a lot more particles, do we have a way to go that we can get someplace safe? So remember, we're still getting the data down, so you'd much rather get less data but then get it rather than get a whole bunch of data and then hit something and then get nothing out of it at the end. So there was a lot of planning that went into what we finally did. Now it turned out that if you actually did the modeling, Charon tended to sweep out the material if it was up there, and so the probability that there was anything there was pretty small. But it took several years to get us to that point, several years where, you know, it was a fair amount of angst, let's put it that way. Now this is when we're leaving, and here's the haze of Pluto, and it's blue. It really is blue. I mean, you know, this comes from the MVIC observations, and if you look at Pluto's haze, it goes up hundreds of kilometers in blue. If you look at it in the methane channel, which is well, blue is about 0.4 microns. The wavelength is 0.4 microns. Methane absorption is around 0.9 microns, so it's about 2.5 times the wavelength of it. You don't see much. You see haze, but it stops fairly far down. And again, the fact that we're seeing these layers, is that because something is forming and then coming down and staying in one place for a while other things occur? Or, you know, what is that connected with? And again, this is the type of work that goes on over the next few years as we get more data and as we learn from that data other things about the surface that can help us point to what's going on there. So here's our timeline. And we're here in the middle of the science playback. We'll do some post-encounter calibrations afterwards, after the playback is done. I mean, this is still a time when we're still sweating things out, because if something happens to the spacecraft, we lose that data. For example, LISA, we did, you know, four high resolution scans and one very high resolution scan. So far we've gotten down 2 of the high resolution scans. So we still have a lot of stuff there. We have a whole bunch of data that we took as we left, looking through that atmosphere, that maybe we can look in that data and see what's in the atmosphere, just like you do on the Earth. Is there methane up there? Is there CO? You know, that sort of thing, because it's a nice long path length that we get from the sun. We did change the direction of the spacecraft after the encounter, because there is a Kuiper Belt object that we've identified that we could get to and do data collection on. And if we hadn't done the change, we wouldn't have been able to do it later on. Now, we have to write a proposal, it has to be accepted, and to, you know, actually do that measurement. So we're not saying we're doing that, but we did the change, because if we didn't do that, it would become a moot point. So, work remaining, lots. We got about 30% of the data down. Most of you guys might not remember this, but back in the day when we had modems that connected us to the internet, remember the 300 baud modems? That's the speed the data is coming down, right? So you just the lines go like this. That's the speed the data is coming down, and we have gigabytes worth of data, right? So it takes a while, and that's physics. It's far away. We can't have a big radiator. We don't have a huge amount of power. It just takes that long to get stuff down. We still have some optimization on the data from the instruments. There can be artifacts. And that's why we're doing that calibration, to make sure that nothing has changed in the time before and after we went to Pluto. We still have to co-register all the data from all the instruments so that we know exactly, yes, when this was seeing that, that was seeing this. We're looking at different angles of things, because not only do particles, the composition of particles change how they absorb light, it's the shape and the size of particles. Once you start getting particles that are sort of the same size as the wavelength of light, they have different characteristics than bigger or smaller particles. And then now we have to go and do our combined modeling, right? We have to take the data that we've got, that we trust, and then go into, say, well, what is the geophysical, compositional, thermal, da-da-da-da-da. In other words, explain what's going on. What is the dynamics that's going on? How is it coupled? Why are we seeing this flat area that's smooth? Is that something that's going to go away after a while? And by the way, as Pluto moves away from the sun, the atmosphere is starting to condense. And in fact, we thought it would be, we were afraid it was going to be gone by the time we got out there. The fact that it's still there is nice. Let's put it that way. And if you're interested in more information, there is this. There's also a photojournal. I couldn't, every time I tried to copy the address of the photojournal, it would mess everything else up. So I said, all right, you guys can just look New Horizons photojournal and you'll see these images. But these are the places to go to get the data from. Now, what time is it? Oh, geez. Okay, so I got a little bit of time. What this is this is a Ralph-centric image movie of what was going on at Pluto, what was happening during the encounter. So remember what I said was we have these fields of view. I'm looking at you. You're Pluto. And now if I want to take a spectrum of view, I have to scan my field of view across you. And now I'm going to go over there and look at you because you're Karen. I'm going to do the same thing. And you're Karabos, and I'm going to do that. And so I have to move around, and I have to change the orientation of things. And I have to do that so that if I take data with Ralph, that I can now also take data with Lori at the same time, or with the Alice, the spectrometer. And by the way, trying to explain to people of a certain age what the relationship between Ralph and Alice is has been a joy for the last 10 years. At any rate, so there's a lot of activity going on, and all that had to be planned because it takes 4 hours for light to get from the Earth to Pluto, 4 hours for information to get back. So if I said, okay, now start to take data, it would say, oh, well, too bad, I'm already past. Because remember, the closest approach really was hours. We were going 10,000 kilometers, or excuse me, 10 kilometers a second, right? So, 30,000 kilometers an hour. You're going by something where you're getting up to 10,000 kilometers with it, that is much less of an hour than, so you have to have everything well planned, and you have to know where things are. That was another thing, is that we were concerned for a while that maybe Pluto was not quite where we thought it was. And so we have this big plan where we take all these data, and it wouldn't be of Pluto, so you'd have to put in more margin, and then that means you take less data because you have to scan more and so on. So what this is shows you what happened during the encounter, at least as far as Ralph is concerned. These long lines are the 5,000 pixel wide MVIC detector, and we scan that across to get color and pan-chromatic. You'll also see a square one, that's the LISA field of view, okay? So, if I'm lucky, and it worked earlier, so. Okay, so now this is, oops, let me get this out of the way. This is 9th of July. So you see we're taking some measurements. Here's the 10th of July. We're taking some more measurements, but that's at least a field of view, and you're really not feeling much of it, right? The resolution is not that great, but we're taking data because we're getting different phase angles. We're getting different information about this. So there is data, there is information in here that's important. Now we're up to the 13th. So we went to the 9th to the 13th in that period of time. Now we're on the 14th. Now we're going to sit on the 14th for quite a while, but look what's happening. Look at all these operations that are going on. And we're doing things like going the opposite way to get flat fields. And we're scanning, there's a scan of Pluto. There's two of our high resolution scans of Pluto. There's one of our high resolution scans of Charon. And I'm not expecting you to follow all this. Just get the idea that there's a lot going on here. This was all planned, not well before, continually as we got to Pluto, as we did practice, as we found out what actually occurred. Now you can also see that, remember how the objects were much smaller than the detectors? Now all of a sudden those detectors are smaller than the objects. So we've gone like a factor of 1,000 in spatial resolution in that time period. That's impressive. Now we're about leaving. This is still on the 14th. Now we're leaving. We're still on the 14th. We're still taking data as we go out. Now we're on the 15th. But all that time in the middle was all the operations that were going on the 14th. So when I say that this was a team effort where the planners and everybody, to get that right, and the fact that we did get it right was amazing. And that picture I showed you was the one that showed the Haze layers, with the mountains and everything. That had to be done in a very specific way because a lot of times we could just sort of fire the thrusters and scan across and didn't have to worry about things. But as we got real close to Pluto, now the spacecraft motion got coupled to the motion that you're doing with the scan. And so now you have to change things at the same rate. So now you have to not only know where you are, but you have to know how fast you're going when you go by and put that into how you're doing the scan, or else you'd smear things. And they did a wonderful job. So I think, actually...
Yeah, I'm sure there probably is lots of questions, right?
But I did it. I got.
Yeah.
And I very much appreciate your taking the time.
And with the questions, if you can try to repeat
Yes.
the questions for the video.
Right.
And okay, questions.
You mentioned thrusters. What was the mechanism for pointing?
Actually, it was
the whole craft.
That's right. It was. There were a lot of little rocket motors, basically thrusters that move the spacecraft around. Now, and a lot of times you'll have spinning objects that can move the thing around, but here we didn't have that. Gyros, thank you, I couldn't remember the name. But here we didn't have the power or the capability of doing that, so we had to use the thrusters. So you'd fire a little thruster and it would start moving the thing, and then when you got up to the speed you wanted, you'd stop firing the thrusters.
And you have enough fuel in the thrusters for all this activity?
That's right, and for what would happen later on. So, yeah. Yes?
When Charon was first discovered, it was considered to be a moon of Pluto. Is it still a moon of Pluto, or is it considered to be two planets that orbit each other?
That's an excellent question, and the answer is the latter. They're all orbiting a central mass location. So if you noticed when on some of the you saw the orbits on that movie I was showing you, they looked kind of weird. They didn't look circular. That's because they were based on the position of Pluto, and as Pluto moves around, it moves around the center of gravity, as do those other moons. So if you plot something with respect to the center of Pluto, it sort of distorts what the other guys look like. But yes, they are considered to be at least a binary system now, hexadecimal system. No, a sextic system. Yes.
With the atmosphere, it was recently announced, I guess, that Rosetta had found on the comet some oxygen. Were they testing for oxygen on the horizons as well?
We would love to. The problem with oxygen is it's not really a strong absorber. Now, possibly some of although I doubt it, possibly some of the plasma instruments might be able to look for it, but we'll see. You know, it was a surprise, and it's not something that we expected at all. And I'd be surprised if it were Pluto, but then Pluto surprised me. So, yes.
How long is the data back? How long is the data back to Earth?
So we started taking, let's say from the closest approach. Basically, we started taking data down the day after, you know, the 15th of July. It's still coming down. We're expecting it to come down through next summer. Right? So it's still another 6-8 months before it's all down. Yeah.
The data.
Oh, I'm sorry. I'm not repeating the question. I'm sorry about that. Yeah. Yeah.
The data transmission coming back, is there any problem with noise?
So the question is there a problem with noise and interrupting the data transmission coming back? And the answer is, as always, there is, because we're taking data into various locations around the world, and if there happens to be rain at one of those places, you can't necessarily get the data down, so you have to dump it down some later time. Or there can be some mechanical problem that causes you, or electrical problem that causes you to skip something, so you do another transmission. You know, that's something that we're always planning on. As far as actually sort of electronic noise, it's been pretty good so far.
But nothing like with solar particles?
No, not yet. Yes. No, go.
What's the trade-off? I imagine you have to go at a certain speed to get there within a career. But what would have been your options? How slow could you have gone so that you've been able to orbit Pluto and not fly by?
So the question is, how slow would we have had to go to orbit Pluto? And the answer is real slow. And the problem is that, so remember that rocket when it took off. Right? That's getting us out of the gravitational field of the Earth and its environment. Well, to stop at Pluto, you'd basically have to have that rocket go in the opposite direction, right? So kind of you need something that's large to slow you down, at that rate to slow you down. So you can imagine that if you went slower, you wouldn't need that big of a rocket, but still you've got to launch that rocket. So it's just really not practical to orbit as we do it with chemicals. Now, it may be that we can use solar electric propulsion, start something, take a long time to get out there, you know, and just continually thrust backwards as we go. But that would be a whole different study. Yes?
This is not a very sophisticated question, but if the Hubble, in the beginning you were showing a picture of the Hubble telescope, and if the Hubble can take pictures of galaxies that are thousands and thousands of light years away, why could it not take close-ups for you from a body that's in the hundreds of millions, say, of miles?
So the question is, why can the Hubble take pictures of objects that are very far away, but when it looked at Pluto, it didn't have that much spatial resolution. Well, if you look at a Hubble picture of a star, it's a point. You don't see any resolution. If you look at a Hubble picture of a galaxy, well, Pluto is 2,000 kilometers, 2,400 kilometers in diameter. Galaxy is 100,000 light years, right? So if I'm looking at light at an angle, that, even if it's far away, makes a reasonably good angle, so I can see something over that area. Pluto is very, very sub-arc second, much lower resolution than most telescopes on the ground, and just barely what the Hubble can do, and that's why it's only a few pixels across. Yes, sir?
When does it finally run out of power?
That's a good question. I've seen various plots, and the idea is that, well, as we go further out, you don't have to run the spectrometers or the imagers because there's nothing to see. So you can back off power there. You can back off power on other things, and perhaps only run the ion, and the student dust counter and things like that. I believe the estimate, and don't quote me on this, but I believe the estimate is somewhere in the mid-2030s that we start to get to the point where we just even can't transmit the data back or anything like that. Yes, sir.
Me?
Yes, yes,
Oh,
ma'am.
okay. I just wanted to thank, I was lucky enough to participate in NASA's social event at Johns Hopkins, and I got to meet a lot of the team and meet Dr. Stern and Dr. Green, who said, you're right, it's 2030s. He said once you start backing off. And it's just been fascinating. Like at 2006, it launched, and just seeing all the images and making Pluto now seem more interesting than it was, than just an icy body. So I want to cause trouble. Are you team planet or team small icy object?
So here's a person who's trying to cause trouble, basically asking me if I think it's a planet or an icy dwarf. So I actually there's a thing on the internet called 4 questions and answer. My answer there was, I don't think Pluto cares what we call it. And the reality is that it's part of a new set of objects that just are going to tell us huge amounts of data. Whether you call it a planet or an icy planet or a dwarf planet, that's a convention, right? It's they used to call, if you look at astrology, I believe the Earth is not a planet, but the sun is, right? So there are conventions that go into things. It's up to you. I just think that it's exciting to go out there and see these things. And, they tell us about what we are. I've been practicing. Any other questions? Oh, yes, sir. I'll get you in a
The
second.
data's still coming in, we don't know. Your talk we'll be looking forward to next summer after the rest of it comes in. But I'm curious, the things that you're seeing and the bizarre things that you're seeing that we can't test with Horizons or New Horizons, what you would like to see from what you've seen so far on New Horizons 2, whenever that might be in the next 20 years.
Well, so then you guys can push for New Horizons too. Obviously, I probably won't be all that involved in it. I think what you'd basically do is have perhaps very similar instruments, but they'd be much more capable now because we have bigger arrays. We can do more wavelengths. We would like to cover more wavelengths. We might want to put on a mass spec, something that can tell us what's there. It would be very nice, and we had actually had in one of the many plans something that would go to the surface. Right now, it doesn't have to land gently, or maybe we can make it so it's an impactor, and as long as some parts of it, that would be something that I think would be extraordinary. Now, the opposite side of that is every time we have one of those that goes into an atmosphere, we find out that it's gone into some unique place, right? So it's not necessarily representative of everything. But if we could see the surface, that would be really nice. And that's something, that you can do without a huge amount of back thrust because it's a small object, right? So you just have to stop it. You don't have to stop the 500 kilometer thing. Kilogram thing. You just have to stop the 2 kilogram thing. And now with technology, we can make that a very capable 2 kilograms. And you had a question.
Can you say something more about the atmosphere and the precipitation out of it, how this impacted planning, how it may have affected the instruments, what they read and so forth. I think this was a critical thing with Pluto, wasn't it? That whole atmosphere, but whether it was going to be gaseous, semi-gaseous, or on the surface or whatever.
So the question is, how did the structure of the atmosphere, the assumed structure of the atmosphere, affect the planning for the Pluto mission from the very beginning?
And the precipitation was coming out of it.
Yeah. So the precipitation is still, it's only coming from a few hundred kilometers up, and we only get to within 10,000 kilometers. So we didn't worry about it in terms of danger. Now, in terms of what we would like to see, how we would do the observations, remember I mentioned that we have that the radio instrument, and also the other instruments that we could take data as we went behind the system. We were worried that if we didn't get out there early enough, one of the reasons we were pushing for the 2006 launch was that the atmosphere would be gone. So it really drove more our impetus to get the launch as soon as we possibly could than anything else. That the instruments were going to be pretty much what the instruments were going to be, because we were going to look for, if there was less atmosphere, we were still going to look for the things that we expected to be in the atmosphere.
How soon will the atmosphere totally?
Well, that's very hard to tell, because again, we kind of thought that it would be gone by now. Now, we were doing measurements of occultation. If a star goes behind Pluto, it doesn't shut the light off immediately. You can kind of see it slowly go down because the atmosphere is scattering light. And we could tell that the atmosphere was still there, and it surprised us. So if there is a mechanism that's causing convection and causing evaporation still from the surface, well, if that can maintain, then the atmosphere can maintain, even though it's not necessarily near the sun. A lot of also what we're seeing is that the colors of things do, so if you've got a black surface, it absorbs more light, it gets hotter. The Sputnik planum, that flat area, is very white. Well, that may be a reason why it's cold. It's also kind of never really gets the sun on it directly. So, that may be why it's still producing things or condensing things from the atmosphere. So stuff may be coming from other places and coming there and forming that flat area. So did that answer your question? Okay.
Yeah.
Any others? Oh, one more.
You have an object that's over 1 billion years old, I assume, maybe several billion?
Yeah.
And you were concerned that the atmosphere might be gone if your mission was delayed a couple more years?
So remember, this thing orbits, right? And Pluto has a very elliptical orbit. So it gets actually inside the orbit of Neptune for part of the time, okay? So the feeling was, well, when you're close to the sun, you get warmth, and that's going to cause the atmosphere to come up. Now as you go far out, now it gets very cold and the atmosphere condenses. So the perihelion was 1988 or something like that. I've forgotten exactly. That's when it was closest to the sun. As it goes out, it's just getting colder. We thought that better get out there soon. Anything else? Well, again, thank you very much for...
This has been a presentation of the Library of Congress. Visit us at loc.gov.